Hello, my name is Caitlin Wigenhorn, and I'm an applications engineer with Texas Instruments in our converters and controllers product line. And today I'm going to discuss understanding the quiescent current spec within our buck converter datasheets. Quiescent current is a critical parameter for always-on automotive applications. For example, a keyless entry system. And it is standard in these applications to expect the IQ to be less than 100 microamps at the module level, and this translates for the wide VN buck converter to be in the range of 10 microamps to 40 microamps. However, even though this parameter is very important, it still can be confusing trying to decode the meaning of quiescent current within a datasheet because there are many different notations and many different types of quiescent current, and this can cause much confusion as to what is the true system quiescent current. Datasheet to datasheet, different types of IQ are highlighted on the front page or even throughout the datasheet, and this can lead to confusion when trying to decode what is the true IQ performance for your system. Generally, when trying to understand this parameter, there are three key measurements of quiescent current that you're looking for. The first is shutdown current. Shutdown current is when the part is disabled, meaning enable is tied to ground and the part is completely off. The second is non-switching IQ. This is when the part is enabled and the feedback pin is tied high, and in turn the device is not switching. This value can be found in the electrical characteristics table and is traditionally measured open loop on the automated test equipment at production. The third kind is switching IQ. Switching IQ is also known as operating quiescent current or no load input current, and this is the IQ that you would see within your system design. Here is an example of calculating operating quiescent current based on the parameters within the electrical characteristics table. And again, this is the current that you will see within your system, the no load supply current. And this example uses the LMS 3655. The purpose of this equation is to take the parameters found in the EC table of the different types of non-switching IQ and add them together to find the switching IQ that will be seen in typical system application. Here, the first parameter will be the IQ non-switching. So again, this is the current drawn at the input pin when the device is not switching. Second is the current draw at the enable pin, which typically is very negligible. And next is the current drawn at the bias pin. And then lastly is the current drawn at the feedback divider, so the current drop between the output and ground of the feedback divider setting the output voltage. Since the divider current and the bias current are at the output, you can use the light load efficiency number to translate to what this current at the output will mean at the input. And here's the example using the LMS 3655 device, and you can see from the EC table the non-switching IQ is 7.5 microamps, and the bias current is 32 microamps, and I would recommend for an application where IQ is the most important parameter, such as a keyless entry application, to use a fixed output variant in order to set this current to 0 microamps. And then once you add this equation together, you will find that the expected IQ switching should be 23.2 microamps. And again, this can be calculated based on those parameters from the EC table and the systems table. Thank you for listening today to join this discussion about decoding quiescent current.